Hello students. So up until previous class, we concluded a major portion of this particular course, and as I mentioned that from today we will start with series solution, right? So we have looked into some methods to solve the second order ordinary differential equation with constant coefficient, variable coefficients, linear independence, dependence, and all those things up until the last class. From today we will start with something called series solution, and when we talk about series solution I will give some definitions, something called regular points, singular points, and all those things, and we'll talk about one or two methods on how to solve these differential equations when they have singular points, and slowly we'll go towards at least a differential equation which yields two very special type of functions, right? So let us start with so usually our we'll stick to second order ordinary differential equation, and it could be of this form, that is p0x, then d square y by dx square, or simply y double dash x, p1x into dy dx, or y dash x, and p2x equals to into y equals to 0, where pi's are functions of x, are functions of x basically. So suppose this is our equation 1, and we basically, so we want we look for the solution in the form of infinite series, in the form solution in the form of infinite series, right? So hence the term series solution. So series solution means that you want to write the solution yx of, let's say, this equation as an infinite series of this type, an into some x to the power n or something. So where an and all these coefficients a1, a1, a0, a1, a2, a3 dot dot and so on. So something like this, where these coefficients they can be determined from the given equation. I mean, we'll see how to determine these constants, right? So our ultimate goal is to write the solution as a in the form of a series, right? And under what circumstances, I mean, what type of series to choose, that we will see one by one. So to first of all, to start with, let me give you some definition. So for example, if we consider let's say this equation itself, but in a general form. So let us consider the linear differential equation LDE of type p0x into yn plus p1x into yn minus 1, plus this will continue pn minus 1 into y1 plus pn into y equals to 0, or some function of x. So we can also have rx, right? So it can be 0 or it can be some function of x, it's all fine. So let us call this as again equation number 1. Now here pi's, so here or where pi's for all I running from 0, 1, 2, 3 up to n are functions of x, are functions of x. Then a point x equals to x0. By the way, this is not initial value, x equals to x0. Usually we denote by zeros, right? So but here it is not actually the initial value, but in general any point. So a point x equals to x0 is called an ordinary point, is called an ordinary point, ordinary point of the equation 1, of the equation 1 if p0 x0 is not equals to 0. That means the leading coefficient should not be vanishing at that point. So then it is called as a as an ordinary point, okay? and a singular point, singular, so S should be small, a singular point of the equation 1 is any point x equals to x1, for which P0 x1 equals to 0. That means the leading coefficient vanishes. So, basically the order of that differential equation will become 1 reduced. So, basically you started with yn, but at that particular point it will become a differential equation of degree n minus 1. So, basically if the leading coefficient vanishes at that point, then it is called as a singular point, and any point which is not singular, which is not a singular point, is then an ordinary point. Not a singular point is an ordinary point, right. Obviously, if it is not a singular point, then it has to be an ordinary point. And then we will also define something called regular singular point. Now, suppose, okay, let us see one example. So, if I give too many definitions, then that is also not good. So, let us see one example. So, suppose we have 1 minus x square d square y by dx square minus of 7x dy dx minus of y is equals to 0. So, here as you can see, our P0 x clearly is 1 minus x square, which is 0, P0 x equals to 0 when, which implies P0 x equals to 0 when 1 minus x square is 0, that means x equals to plus minus 1, right. So, at x equals to 1 as well as minus 1, P0 x vanishes. So, therefore, x equals to 1 and minus 1 are the singular points, and the domain D equals to all such points in R which are not equals to x 1 and minus 1 are the regular points, right, regular points. So, except these 2 points, all the other points on real line will be the regular points. Okay. Similarly, if we have equation of this type, so here we have 2 singular points. If we have equation of this type, x into d square y by dx square plus 5x dy dx plus 7y is equals to 0, then here P0 x is x and that vanishes at x equals to 0. So, P0 x equals to x, which vanishes at x equals to 0. This implies that 0 is the singular point and that is unique, singular point. So, that is the only singular point. So, suppose if you have x into x minus x cube, right. So, then you will have 0, 1 and minus 1, x minus x cube. So, that is, if that is your P0 x, so then in that case you will have 3 singular points. So, how many singular points you have, that we cannot say, because it depends on what kind of expression that is given to you. So, it can be 1, it can be 2, right. And if we consider equation of this type, d square y by dx square plus 5x square dy dx plus 17y equals to 0. So, this equation has no singular point. This equation has no singular point, because for all x in real line, the leading coefficient P0 x is 1 and that is then vanishing. So, basically it has no singular points, right. So, all the points on the real line are basically the regular points. All right. Now, let us suppose that the point x equals to x0 is a singular point, of the equation p0x y double dash x plus p1x y dash x plus p2x y equals to 0 with polynomial coefficients. So, p0, pi's and p1, p2 and so on, they are polynomial coefficients. So, then p0 x equals p0 x0 equals to 0, and hence px has a factor x minus x0, right. So, this is a factor x minus x0 with some power. So, it can be x minus x0 or it can be x minus x0 whole square, we just do not know, but it could be a factor like x minus x0 to the power m can be 0 or some other real number. So, this. Now, if we divide dividing both sides of this equation by x minus x0, then what will happen? X minus x0, then what we will get is, we will get y double dash x or d square y by dx square plus capital Px. So, capital Px will be now p1x by x minus x0, right, and to dy dx plus capital Qx into y. Now, x equals to x0 is a singular point, and now x equals to x0 is a singular point, and Px and Qx are rational functions. Hence, at least one of capital Px and capital Qx or both have a dominator involving the factor x minus x0, and we reduce. So, here basically, here x equals to x0 is a singular point of 3, is a singular point of I do not know which equation number was that, was it 3? Let us put star, singular point of star if the denominator of Px contain x minus x0, obviously, because then you multiply x minus x0 all sides of the equation, and then you will have Px in the leading coefficient will involve then x minus x0, right. So, then that will be our Px which P0x which vanishes at x0. Earlier what we did, we divided by entire P0x including the factor x minus x0. So, there is a factor x minus x0 times some other terms which is remained from P0x, and this entire thing we are calling it as capital Px. So, P1 by x minus x0 into whatever remaining polynomial is there, that is denoted by capital Px. Similarly, capital Qx and so on if it has more terms. Okay, and if Px does not contain, if the denominator of Px, if Px does not have a denominator, containing x minus x0, to a power higher than 1, and if the denominator of Qx does not contain the factor x minus x0 to a power higher than 2, then x equals to x0 is called regular singular point, and if x equals to x0 is not a regular singular point, then it is an irregular point. So, let us go back. We have regular point, or we have ordinary point, then we have singular point. Within singular point, we have regular singular point or irregular singular point, right. So, regular singular point and irregular singular point. So, for example, if we consider this x minus x1 square into x plus 3 y double dash plus x square y dash minus of x cube plus 2x plus 1 into y equals to 0. So, here we can determine our capital Px as x square by x minus 1 whole square x plus 3. So, this will become x by x minus 1 whole square x plus 3, and capital Q will be Qx will be minus of x cube plus 2x plus 1 divided by x into x minus 1 whole square x plus 3. So, here we can see that x equals to 0 as far as P0 x is concerned, x equals to 0, x equals to 1 and x equals to minus 3 are the singular points, right. Except them, all the points are regular points. Now, the factor x is absent from capital Px, and it occurs to the first term of capital Qx in the denominator. Hence, x equals to 0 is the regular singular point, right. So, that means in the denominator, if it is not present for power more than 1. So, then in that case we will have x equals to 0. So, here we can write the point x equals to 0, 1 and minus 3 are the singular points, right, the factor x minus 0 is absent from the denominator of capital Px, and it occurs to the first power of the denominator of the power of the denominator of Qx. Hence, x equals to 0 is a regular singular point. right. So, this is how we determine the regular singular point, whereas x equals to 1, that is x minus 1, that factor is still present here. Where is that? Here in px with power more than 1, and similarly it is present in qx. So, then x equals to 1 and is basically irregular point. So, here we can write the factor x minus 1 appears to the second power in the denominator of px, which is not allowed or which is not permitted. So, hence x equals to 1 is an irregular singular point, and similarly x plus 3. So, x plus 3, where is that? Let us write here. X plus 3 appears to the first power in the denominator of px, and to the first power of qx. Hence, x equals to minus 3 is a regular singular point, right. So, we have seen one example, basically this one, and for this example we know that there are 3 singular points and we categorize them whether they are regular, irregular singular points, right. Now, there is one more small definition. A function f(x) is said to be analytic, or regular if it can be represented by Taylor series summation and running from 0 to infinity fn x0 divided by factorial n x minus x0 whole to the power n, which converges for all x in some open interval, and this series basically converges for all x in some open interval, of course containing x0, right, in some open interval containing x0, right. So, we have defined also Taylor series, or analytic function, or analytic, well, when you say analytic we usually relate it to complex analysis, but for functions of real variable also we can use the term that is called analytic. Okay. Now, we more or less got the idea what is a regular point, what is a singular point, what is what is ordinary point, what is singular point, among singular point, what is regular singular point, what is irregular singular point, and so on. So, now I will solve one or two examples just to tell you how does the solution of ordinary differential equation goes when we have um, regular points and sorry, when we have ordinary points and when we have singular points, right. So, the idea is that so again we will stick to the second order equation. So, suppose we have d square y by dx square plus capital P x into dy dx plus q x y equals to 0. Let us call this as equation number 1. And here capital P and capital Q are the functions of x. Now, let us choose y and dy dx takes the arbitrary values a and b, and then basically so let us choose or let y and y dash take arbitrary values a and b respectively. So, then respectively at x equals to 0. So, we have from 1 d square y by dx square equals to p x dy dx minus of q x y. So, there is a y missing here, minus of q x y, right. Of course, there is a y, sorry. So, this equals to 0, like q x y, not q x equals to y, q x y equals to 0. So, then I am saying d square y by dx square equals to, I will take everything on the right hand side. Okay. Now, since p x and q x here we do not have any singularity or they are not undefined at x equals to 0. So, then we can write, we can compute d square y by dx square. So, we can compute d square y by dx square at x equals to 0, because it is how to say not undefined, because p x and q x, they are both non-zero at x equals to 0. So, then in that case it is just an ordinary point, and therefore, it can be computed that d square y by dx square equals to p at x equals to 0, dy by dx at x equals to 0, then q x at x equals to 0, and y at x equals to 0. So, we can compute d square y by dx square. Now, we can also compute d3 y by dx cube at x equals to x 0. So, this can also be computed at x equals to x 0. We have to just take the chain rule. So, that is minus of p x. Oh, this is minus, no, sorry, the minus of p x into d square y by dx square minus of p dash x into dy dx minus of q x into d square by dx square and minus of dy dx into q dash x, right. So, this. Hence, we can find out d3 y by dx3 at x equals to 0, because we know our d square y by dx square at x equals to 0. So, this will keep on happening. So, we are basically doing this method of induction in a way, and you can obtain the value of d4 y by dx4, d5 y by dx5 and so on. So, if we keep doing that, then we can compute successively dn y by dxn, right, at x equals to x 0, and so here we at x equals to x 0 we can compute dn y by dxn, and therefore, if we put all these values, so we can we can put the values in Maclaurin series. Therefore, the Maclaurin series will be yx equals to y 0 plus summation n running from 1 to infinity summation n running from 1 to infinity xn by factorial n dny by dxn at x equals to 0. So, now we have yx as an infinite series of y0 plus summation n from 1 to infinity x to the power n by factorial n dny by dxn, right. And the right hand side of 4 will converge to yx throughout some interval, throughout the some interval. The right hand side of double star, the right hand side of double star will converge to yx without any trouble converge to yx without any trouble, and without any trouble throughout, will converge to yx without any trouble throughout some interval about x equals to 0. So, if we can calculate all these derivatives, that means if your curve is smooth, then in that case or if your y is smooth or well behaved, then we can calculate all these derivatives, and therefore, we can calculate the right hand side, which will be converted. So, thus we are looking for the solution of the type yx equals to summation n running from 1 to infinity or even 0 to infinity an into x to the power n, where an will be dny by dxn into 1 by factorial n and so on. So, we are looking for a solution of this type. This is the infinite series for which we are looking for the solution. But this happens when our P0 is non-vanishing. When P0 is vanishing, then there is an extra x to the power, let us say m, that needs to be multiplied with the solution. And if we have x equals to x0 as the singular point, then we have to multiply something like x to the power m into this sum to get the solution. So, if we have a regular point, if we have ordinary point, then this expression will work. If you have singular point, then there is a special form, that means you have to multiply this series by x to the power m or x to the power rho. In some books they use rho, and then we calculate the solution. Why do we have to multiply by x to the power rho? That should be that basically follows from the calculation itself, that if there is a singular point, then this is not the ideal choice for the series solution, because then all the ans will become 0, hence yx equals to 0. So, we do not want all the ax to become 0, all the ans to become 0, and that is why when we have the singular point, we multiply this solution with some x to the power m type function, and then we sort of calculate the solution of this infinite series, right. So, I try to give some definition, some basic idea about the ordinary solution and singular solution. I will stop here in today, but we will continue this discussion, and in the next class we will solve 1 or 2 examples just to get familiar with what do we mean by these ordinary points and singular points and so on. So, thank you for your attention, and I will see you in the next class.